Welcome all to the 7th edition of the Geoscience Remote Sensing Society Young Professionals and International Society of Photogrammetry and Remote Sensing Student Consortium's Summer School. Well, this edition has for the first time a combination of webinars, roundtables, and tutorials with hands-on, and is organized by two Santa Catarina State universities, UDESC and UNO Chapecó. This event is supported by two scientific societies, the Geoscience Remote Sensing Society, the International Society of Photogrammetry and Remote Sensing, and their student branch, the Young Professionals one from IEEE, and the Student Consortium from ISPRs. We welcome you all to check our welcome words given by the president of those scientific societies and also the rectors of UNO Chapecó and UDESC. We also welcome you all to answer our quiz in both English and Portuguese languages about some particularities about Santa Catarina State and also southern Brazil. This year, this event is supported by the Santa Catarina State Foundation, FAPESC, and two private companies, Canoinhas Geoassessoria and Instituto Gilson Volpato de Educação Científica. This event is being shared and promoted by different universities and institutions from Brazil. And so far, we have already 8 webinars, 2 roundtables, and 2 tutorials with hands-on. Today, we will have a talk about global vegetation trend, a multi-decade planetary coverage and analysis-ready product, given by Dr. Leandro Parente. And we also invite you for next Tuesday for a webinar about SAR polarimetry and multitemporal SAR statistical descriptions, given by Carlos Lopes Martinez. For today's activities, I would like to invite Professor Laerte Ferreira. He is a full professor at the Federal University of Goiás, and he will be introducing himself and also the co-chairs and our main speaker for today. Professor Laerte, so the room is now yours, and in the name of the Brazilian chapter of the Geoscience Remote Sensing Society, I would like to acknowledge you, to thank you for actually accepting this task.
Well, thank you very much, Dr. Geraldo Lisenberg. For me, it's a great pleasure to be here today for a very personal reason. Dr. Leandro Parente, who is the invited speaker in this today's session, is a very good friend of mine. And so for me, and of course, that I'm very curious to learn about the amazing work Dr. Leandro is conducting together with his colleagues at the OpenGeoHub Foundation in the Netherlands. But first, I want to give my most warmly welcome to Dr. Eliana Fonseca, who will be co-chairing the session with me. Dr. Eliana Fonseca is a professor and researcher at the Federal University of Rio Grande do Sul in Brazil. And she's at the Department of Geography. So it's very nice to be here with you, Dr. Eliana Fonseca, sharing this chair of today's session. So please be very welcome.
Thank you.
I also want And please, sorry, I'm not very professional at this, Eliana. So please, Eliana, if you'd like to say a few words.
Oh, thank you. It's a pleasure to be here with my colleagues, my Brazilian colleagues.
Okay, great. And now I want to give my most warmly welcome to Dr. Leandro Leal Parente. As I said, I'm very fortunate to be a good friend of Leandro, who is an amazing young scientist. So I think it's a privilege for all of us today to hear what Dr. Leandro Leal Parente has to say to us about vegetation trends, global vegetation trends based on MODIS data analysis. And more than that, Leandro, together with his colleagues at the OpenGeoHub Foundation, is working, is focused on producing product-ready canopy trends or global-ready products for vegetation analysis. So I think that, not I think, I'm very certain that what Leandro has to show us today is of most interest to everyone in Brazil working with vegetation remote sensing. And besides showing what he's working right now regarding time series processing, Dr. Leandro Leal Parente is going to provide us, is going to share with us these products or provide us with his access to the products that the OpenGeoHub Foundation is producing. And those are amazing products. Just before we entered the room, we were discussing, well, in the backstage, saying that I was saying that I have much to learn with Dr. Leandro Leal Parente because the work he's doing regarding remote sense science, remote sense data processing, particularly focused on time series analysis based on machine learning approach, different machine learning approaches. This work is really the cutting edge of what we can expect in terms of optical remote sensing applied to vegetation monitoring. Dr. Leandro Leal Parente's background is in computer science, but after getting his degree in computer science at the Federal University of Goiás, Dr. Leandro Leal Parente got both his master and doctorate degree in environmental science. So I would say that Leandro is a mixture of, is a very good mixture, a very rich mixture of an environmental scientist with a data scientist, remote sense scientist, and a computer scientist. So it's, I think, a perfect combination, and that perfect combination is resulting in great remote sensing products. Well, thank you again, Leandro, for accepting the invitation of the Geoscience and Remote Sensing Society and the ISPERS for this series of webinars for young professionals. So it's a pleasure to be here, and it's a pleasure, it's a great pleasure to have you here. Leandro, the word is yours. Thank you.
Okay, thank you, Laird, for this very warm welcome. And I would like to say that it's an honor, like, be here to give this talk. So I haven't organized by IEEE, Geoscience and Remote Sensing Society, and the International Society for Photogrammetric and Remote Sensing. So, and for me, I'm very glad to share all this product with and approach with you. And I would like to thank you also the Dr. Veraldo Lindberg for the invitation, and I would like to grant the Dr. Eliana Fonseca to help with the moderation of the session. So I will share my screen now. And are you seeing my screen?
Yes.
Oh, yes.
Okay.
And Leandro, just a quick note to say that you have about 60 minutes, up to 60 minutes. And then after Leandro's talk, we are going to have about 40 minutes for questions from the audience. And we will be glad to take those questions so we can have a brief debate around the ideas, approaches, and products that Leandro is going to present us. Leandro. Thank you
Okay.
again, and good luck with your presentation.
Thank you, Laert. And so on the bottom, you can access the link for the presentation. I think it's also in the chat. So today I will talk about global vegetation trends and a product that we are developing here on the OpenGeoHub Foundation, covering 2 decades and for the whole planet. So my presentation will be divided in 2 moments. So I will talk first about the short introduction, the motivation behind this product. What is the processing workflow that we implemented here, the results that we produced, and all these results are publicly available, and I will show how to access this data set. So there are multiple layers, and I will show how to access it with a hands-on tutorial through using QuantGIS and Python scripts, and the code is also in the presentation. And by the end, I will just present what are the next steps and some final remarks of what, how we plan to use it and what are the scientific implications of what we are doing here. So first, I would like to start with the scientific background. And so it's important to explain what is a vegetation index. So it's something that, it's a concept that it's very well known by who works with remote sensing data, but I like this paper from, it's a classic paper that evaluated the relation between wet biomass and some Landsat spectral bands. And here we can see the red band and the near infrared. So the dots are related with field points. And in this paper, Jim Tucker evaluated several spectral indices, so different linear combinations of these bands, including also the green band. And testing all these linear combinations, he found like some a very nice correlation for some of these linear combinations. For at the time, it was not like really a spectral vegetation index, but we can say for sure that this is the part of the normalized difference vegetation index. So NDVI, it's a very well known index that combines the near and the red band, and you can see here the high correlation with the wet biomass. So, but this paper worked only like for some specific sites, and other classic paper about vegetation index. And here we can say that this is a paper that introduced a global vegetation product derived by modes, derived using modes data, and it's from 2002. And this paper, it's also like very well known. And in this paper, they explain how the modes data were like was organized for the whole planet, and how they delivered it through the NASA website. So it's a remarkable work, and at the time was a kind of revolution in the remote sensing field. And here you can see the NDVI, and the EVI, it's a other vegetation index that includes the blue band, and you have also the quality assessment band for all the pixels of the planet at 1 kilometer. And so with this modes product, several collections of the product were like developed. And if you think about the concept of the collections, a collection in modes, it's a kind of it's a new workflow and new methods and new ways to process the data, but that's recompute all the past images. So a collection, it's a full data set of images that with methodological improvements. And this paper from 2017 found like a significant difference between collection 5 and collection 6. So, and it explained that it's really important to have this concept of collection because we can they can implement new improvements and correct some problems and deliver like better results. And using these two collections and this difference, this paper discuss about if the planet is becoming, it's browning or greening. And according to the collection 6, like the most recent data of modes, the planet is becoming greener. And it actually correlates with other satellite data, so AVHRR and the spot images. And in this paper, more recently, they analyzed what are the characteristics, the drivers, and the feedback of this greening phenomenon of the planet. So it's a kind of fact that the planet is becoming greener, but it doesn't mean necessarily that it's a good thing. And in this paper, we have the key points that explain this phenomenon. So of forestation and agriculture intensification in China, India, CO2 fertilization in the main drivers of the global vegetation greening. So warming in boreal and Arctic zones and biomes, but this of course has this warming can produce a negative effects on the greening in tropics, and the greening enhance transpirations, a process that reduce soil's moisture and runoff locally, but on the other hand, it can change the local precipitation patterns. So there are several implications of it, but if you think, so why the planet is becoming green, so it's a deep discussion. But if you think about the land use and the land cover change, so we know that the planet, the humankind, it's really changing the landscape. But if you see this data here, so it's a very recent paper that explains that the global land use change are 4 times greater than previously estimated. But still, if you just look if you're not considering like multiple change events, just 17% of the planet it's actually changing. So you have a lot of land cover and land use changing in a kind of the same place. So there is this dynamic. And on the other hand, we can understand, and we can look in this data, we can understand that 83% of the planet has a stable land use and land cover since the 60s. And in this product, it's a Hilda Plus. It's developed by University of Wageningen University here in Netherlands, and they combined like different remote sensing data and census data to reconstruct the land use and the land cover of the planet since the 80s. So if we think that we have all these stable areas, so a trend analysis applied to the global vegetation products can help in the monitoring of the Earth's stable areas, as for example, to map land degradation across the world. So that's one of the applications. So with this motivation, we started to look and to try to access and this vegetation index products. And if you, for example, for modes, if you try to access it, you have two ways to access. One is do like a direct download to using the USGIS or NASA tools, and you can access like the tiles of the modes with multiple bands, and those are individual files, and you need to process it by download and process it by yourself. And of course, we can also access this data through the Google Earth Engine. So using this cloud processing technology, that it's a very nice trend in the remote sensing applications. And here it's an example of the ProbaV product. And to export the data for the Google Earth Engine, you can use like Google Drive and Google Cloud Storage. But if you think even using the Google Earth Engine, it's just like the original product that you have in this main repository. So to really process it and to really run some analysis, like a trend analysis and other types, including, for example, machine learning analysis, there is a lot of work. So you need to process it and organize the data. And if you download, you need to do a lot of, you need to mosaic, you need to remove the clouds. But this is actually like a problem, not only of the vegetation index data sets. You have, today we have multiple sources of Earth observation data. So here we are seeing like MODIS, Landsat, Sentinel, PlanetScope, and we have other satellites also. So, but the most part of this data, it's not real analysis ready. So, and this is a kind of a issue if you plan to perform some environmental analysis and to really use this data to derive some scientific knowledge. So it's important, and we understand that it's a challenge that needs to be addressed. And what it's really necessary, considering all this data, we need to like remove the artifacts, remove the clouds, remove cloud shadows. And when you remove all these pixels, contaminated pixels, you need to perform some gap fill operation that does not introduce bias. And after that, it's possible also organize this data in a way that more people and other researchers and organizations can access it and derive like new products on top of it. So, and there is a link here for a nice podcast that the problem with the satellite data is that it's not a commodity. So we think that it's a commodity because we have multiple sources, but just to put all this data together, or considering just one satellite, it's a lot of work to organize it and to start doing some scientific analysis on this data. So we need to transform it on a commodity, and that's what we are trying to do here. So considering it, we organized these 3 goals. So the first one is develop a reproducible workflow able to process multiple vegetation index products. So AVHRR, modes, ProbaV, and here I will present the results of for MODIS. And produce a complete, consistent, and analysis-ready vegetation index data set. So cloud-free, gap-filled, without artifacts. So and after all this processing, all this workflow implementation, and the last goal is really put it in deliver this data through like a recent data formats and protocols. So now we have Cloud Optimized GeoTIFF and the stack standard. So we believe that if we put this data really available in a nice way, we can improve the usability of this product. So, and of course, we plan to do it using like a reproducible research standard. So it means that everything that we are doing here, getting the data, processing it, removing the clouds, performing the gap filling operation, and do this trend analysis, everything of course, we are implementing by code, but the code, it's available, and other researchers and other organizations can access it and change it and implement new approaches on top of it. So we believe that we can evolve together and help and improve the remote sensing field if we really implement this reproducible research standard. And so, considering it, we develop a processing workflow that mainly combines the Earth and take advantage of the Google Earth Engine platform. So we created like a code to export all the modes, 13 key one, the EVI, so the Enhanced Vegetation Index version 6. So we exported this data from Google Earth Engine because the data is there and we can export like quicker than downloaded everything. But it's possible download everything. We already downloaded it. But in this, in the beginning, we used the Google Earth Engine because it's better to export just one band. If you download the data from NASA, for example, you need to download everything, all the bands. So, and using this product, we mask the low EVI value. So we used the pixel reliability band, values bigger than 1, we removed them. And using, here we aggregate all this data. So it's a 16-day product, but we aggregated it by a bi-monthly time series. So we produce it from 2000 to 2020. For every 2 months, we produce like one image with gaps till here. So after that, we downloaded it and we removed the outlier values, and we performed a gap filling operation. So because we have gaps, right? Removing the clouds and the cloud shadows and some artifacts. So I will show you how the data looks like. And after that, we performed a trend analysis considering just the trend. So as we have now a complete time series, we used like a classical approach to decompose the time series in season, trend, and residual. And using just the trend, we calculated like an ordinary least squared regression for each pixel of the planet. And we saved all the parameters and the of this regression, including the R-square and the beta or slope and the alpha or intercept. And of course, we are doing all this processing, so it's important to save each part of this step because, for example, just the gap-filled time series, it's a product, so other analysis can be performed on top of it. And we also saved the time series without the season. So I will show some examples that it's a kind of, in this data, you cannot see like the interference of the precipitation regimes and the changes in the for example, in the savanna vegetation. So because the seasonality was actually removed. So this is the result of what we exported from Google Earth Engine. So you can see there are some gaps. And so we used our internal computational infrastructure, so it's almost 400 threads. Now we have more, and we gap filled all the dates here. So it's a every 2 months product, so it's a bi-monthly product. And here you can see how the Earth is actually breathing. And because this, you can see this seasonality effect and how, for example, in the tropics, the vegetation is changing because of the precipitation regimes and the temperature regimes. And so we produced it for 126 dates, so it's a big image, but we organized it in a nice way to access on a global scale, and I will show to you in the hands-on part. So using this gap-filled operation, gap-filled data set, we, so here it's example, we performed this classical operation to decompose the signal in trend, season, and residual. And considering just the trend that we can see here, so this is actually real data for this point. It's located in the Mato Piba region in Brazil. So it's a big agriculture point area, and the point it's located in this big agriculture area. And using just the trend, we performed a regression, simple regression. And here you can see the trend. So we performed the regression, but we saved also the trend result. So it's for every pixel of the planet, we saved all these time series. So here we are seeing for 1 pixel, and here we are seeing it for all the planet. And you can see that in some place you can see a small variation, but we believe that this trend can reveal some land degradation process. So it's what we are working and analyzing now. And here you can see the beginning and the end of the time series. So this, the image here, it's from the 2 months of the end of 2020. So November and December. And the first one is January and February of 2000. And so this, considering just this trend signal for every pixel, we trained a regression. And here we can see the direction of this trend. So the green areas is where the trend is increasing, and the pink areas are where the trend is decreasing. And so the result matches with what we found in the literature. So the planet is actually, it's really becoming greener. And here it's just an overview. When you zoom in, I will show it to you. When you zoom in, you can see like real difference between like patches and some, for example, crop fields that are decreasing and others that are increasing. But and we will work with this data also during the hands-on part. And I mentioned to you that we saved also the regression parameters. So here we can see only the pixels that have R² bigger than 0.25. And we also saved like the p-value for the slope or beta, and where we have the significant value for the regression analysis. And here are some examples. So if you zoom in here in this central part of France, you can actually see in the landscape some areas that are becoming greener, and that are and other areas that you can see the decreasing signal in the trend. And in blue, you have the gap-filled result, and in green, it's the trend, just the trend signal without the season. And in red, you can see the regression result and the confidence interval around the estimation. And here in Brazil, you can see, again, some in this chart in the bottom part, probably it's a conversion of to cropland, and maybe first for pasture and later for crop. And on the other plot in the top, you can see like an improvement in the cropland or agriculture productivity. Maybe it was pasture and it was converted to soybean or more like an animal crop because of the signal. And here in China, you can see some of the crop areas becoming with the positive trend. And here maybe in this where you have like where we have this negative trend could be some urbanization phenomenon. So in this region, but this is just like some small examples, and of course this is we can analyze this data from different aspects. But for example, you can use some other land cover maps just to map where are the stable areas and analyze it, or you can perform like some like breakpoint analysis considering algorithms like BFAST on using the gap-filled signal. So there are a lot of possibilities of how to analyze parts of the data that we are presenting here. And so now it's time to access the data. And so it's important to explain the technical aspect of what we are doing here. So we downloaded all these MODIS product and we processed all these operations and generated like several global layers. But most important, after that, we produced Cloud Optimized GeoTIFFs. So if you think in this format, it's a kind of evolution of regular GeoTIFF, but it allows basically the random access, so you can access just parts of the data, considering, for example, a specific geographic region, or you can access like the whole data, but using like a small resolution overview of the data set. So I will show it in practice. So, but it's important to understand that we produced this format. We organized the data in this format. It's a new format, and we hosted it on a cloud objective storage, so using a S3 standard, but you can access it using the HTTP protocol, and we will do it during the hands-on, and you can access through Python or any programming language. So, and you also can access through regular geospatial solutions. So, because actually all this access is implemented by the low-level library GDAL. So what we will do in this demonstration is we will access the overview. So considering all the planets, so the whole globe, we will access like a kind of low resolution representation of this data set, a kind of 10 kilometer that allow us to see and to analyze the data. So it's not the full resolution, but it's a pre-processed low resolution image that is embedded in the Cloud Optimized GeoTIFF. And after that, we will select like a region of interest and perform like a clipping operation. So, and save it on the local machine. So, and you can reproduce it and do by yourself in your workstation. And it's a very nice way to access, for example, just a part of the data for a specific region, and after that perform some analysis for your study area, for example. And lastly, we will present the time series analysis for one pixel. So for a specific coordinate, we will retrieve the trend signal and the gap-filled signal and plot like this chart to analyze to actually see this result, but on a temporal domain. So as I presented here, so you can, in the demonstration part, you will be able to do it for any part of the planet. And to do it, I created this script. So it's a notebook. It's a Jupyter notebook developed in Python. And I will open here. And it's important to say that a lot of the functions that I will present are in this EUMAP library. It's a library that we are developing here on OpenGeoHub in the context of the GeoHarmonizer product with some other partners of the project. So you have different ways to access the data using this library, and you can perform, for example, the same gap filling operations that we performed here and do like machine learning. But I think it's a nice way to access, for example, the data set that we will present here. But we have also different tutorials specific for Europe, but you can use this code and the library for other image that you have, for example, for your study area. So I will enter here. I will just enter first in this repository here. And here we have the two parts of our workflow. I will not explain it, but this first code here, it's to export the modes data from Google Earth Engine. And this other code here, it's to script, it's to process and to do the gap filling, perform the trend analysis. So we have everything here and it's publicly available. You can use it for other regions. And of course, we can improve the product and reprocess everything from scratch if it's necessary and with some methodological improvements. And here you have like the data access Python notebook. So, and this is a open repository with several global layers that we are preparing here in the OpenGeoHub. And you can access this layer through our web viewer, OpenLandMap. So you can download this code and start executing by yourself. And before start, I want to explain just that we have these installation instructions of how to use the UMAP. And here I'm using like an environment that it's prepared with the new GDAL versions and all new GDAL version and new Raster versions and several GIS packages in the Python environment. And you can use it also to do your analysis in Python. We have also like a container in R. So you can use this Docker image and just use it in your workstation. And here there are some instructions of how to set up it. So I will not do it. I'm already using my preset up environment, but I think it's important to explain that you can do it by yourself to run properly the code that I will present here. And so this is the code that the script that I will run and explain to you. So remember that here we will access all these data sets that we produced. We will access through HTTP using because we have everything as Cloud Optimized GeoTIFF. So here is an explanation of the approach, what we did, and you have several links here to access, for example, exactly what is the algorithm that we use to apply the deseasonalization operation and things like that. Here is a short explanation of Cloud Optimized GeoTIFF. So let's start. And first, we will import the functions and the models that we will use here in Python. And you can see that we have these functions here. And I created several functions here to help us. So in the notebook, we will just call some of these functions as this one that produce like the URLs to access the files. But and later you can check it and see how it was implemented under the hood. So first, I will show to you this 4 functions. So here we are seeing like we have a function to generate like the address, like the remote address to access this data. So you can see here it's a valid URL. So it's hosted in this Wasabi. It's a S3 alternative. So it's a cloud object service, and we can access directly the data from there. And you can see here it's the gap-filled data. So it's a kind of the input data for our approach. For the gap fill, we also have this flag. It's a kind of metadata where we did the gap filled for the pixel to understand what pixels are like interpolated and what pixels are really real. And here you have the trend. So it's just the trend without the season. And you can see that this method, it retrieves like 126 files. And here I'm just presenting the first one. So for example, you can change the index here, and you see that here we are seeing another date. So this is actually like a temporal, it's a time series of URLs that we will use to access the data. And for the regressions, for the regression data set, so the output of the regression, we generated several parameters here, but it's not temporal, right? So we just performed like this regression analysis across the whole time series. And here in the file naming convention, you can see the 2000 to 2020. So these URLs are like temporal. So we have one file for every 2 months. And here we just have like the final output of the regression. So it's a kind of long-term response of the vegetation index. So what I will do now, I will just copy this URL here and open it in the QuantGIS. So I have my QuantGIS open, and you can add like a regular layer as a layer that you have, for example, in your local workstation. But it's important to explain that here you will access like local files, but you also have this option here like HTTP, cloud, etc. And I will just copy the URL to here. So, and when I click and add, it takes like 5, 6 seconds. And okay, I will close. And here is the data. So what is happening here is the QuantGIS is accessing like the data that it's hosted on the cloud. So I don't have this file in my workstation now. And if you use, for example, this tool, you can see that you can actually check the values. So this is not like just a PNG or like a visual representation of the data. This is actual the data that we processed and I can access it through cloud and without have the data here. And I will show how it works like in the Python part. So you can work with this data as you do like with any regular layer. So I will just improve here the visibility, and here it is. We have like this color representation for the EVI, and green is where we have like higher EVI, and you can zoom in and it will access the data. And for example, you can zoom to the full resolution and you have full access. I will just put like a satellite image here to compare with the result, and we can see that it's matching with the landscape. And again, you can check the pixels and you can see like the pivot areas here. And during the processing, we removed like the water. So you see all these missing pixels are like, it is because we removed these pixels like, according to our land mask. But of course, you can go for other parts of the planet and you have all the data here. So how it actually works, right? Because it's a big data. If you check the number of pixels here, we are talking about the whole planet at 250 meters. So it's a big image. And so to understand how this is possible, we will access I will present how to access the overview. So as I explained it, the overview, it's a low resolution representation of the data set. So when we generated all these cloud optimized GeoTIFFs, we performed like several we processed all these overviews considering different resolutions. So when you open the data to see the whole planet, you are checking like a image that has, I don't know, 5-10 kilometers. It depends, but that image was processed considering the full resolution data. So, and this is the way, for example, of Google Earth Engine organize like inside of the platform all the image archive, and you can, for example, run your code and see the result on the fly. So it's the same principle. So you have like a short representation, like an overview representation of the real data set that it's pre-computed. And here I will show how to access this representation in the code. So this overview representation. And it's important to explain that you can access the metadata information. So you can access all the like the headers of this GeoTIFF file. So you can see how much is the size of the image, what is the projection system, without actually reading the data. So here you can see that I'm accessing this remote file and I have all the properties here. So it's one band. I have all the size of the image, and we can see the compression algorithm and things like that. And for example, if you multiply the width and the height, you can see the total number of pixels. And so how we can access this overview? So I created a method inside of that access.py, and you can check there, but it's mainly using like Raster that use the GDAL and that access just like the different levels of pre-computed visualizations that we have for the data set. So here, for example, I will access it, and you can see there's multiple overviews, representation of this data. But when I access it in this Python environment, the image it's way less. It's less data. So I'm accessing just like an image that it's 1,000 by 2,500. So this is the overview dimension. So it's way different of the original and the full resolution data set. But what it's interesting is this, it's actually real data that was like just downscaled, considering like an average of all the pixels in the full resolution. And you can see this overview, and you can have like a nice representation of it. So this is what, for example, QuantGIS is doing to access the data. And of course, you can iterate over different URLs, and you can see like multiple representations, multiple dates of the data set, and here it's the name. So this is a very nice functionality of Cloud Optimized GeoTIFF. And for example, you can use this data to actually compute some analysis. So I could perform like a trend analysis just in this overview representation, but it's a real data, but it's just like in a low resolution. So, but of course, we processed it in a full resolution, and it's important to explain how we can access it in a full resolution. So to enable that, I will use this package here just to put in this environment like a web GIS functionality, so we can zoom in some place. So I will get a region here, and I will draw like, so I'm selecting this region here, and I will just read this data, but at full resolution. So considering this extent, this polygon, I'm generating this bounding box, and here we have like a window representation. It's just like like the address of this region in the raster file. And here I will access the data. So actually, this is a full resolution image. So here I'm accessing, like sending just that region, but I'm accessing the real data that it's hosted in the cloud. So, and it's really fast, considering the amount of data that we are accessing here, and that you can. And of course, if you put like a bigger region here, probably it will take more time. And let's see like now the last image of the time series. So here you can see the beginning of the time series. This is the gap-filled data. And here you can see the end of the time series. And of course, you can iterate over it and retrieve the data. So it's a kind of raster database that you can access any part of the planet and in a quick way, and start doing, for example, processing Python or saving the data, as I will show in the next examples. So here I'm accessing now the ordinary least square regression output. So this is the trend, the result of the trend analysis. So where we are seeing like green areas, it's mainly because we have an increase in the vegetation trend. And where we are seeing like pink areas, it's where we have a decrease in the vegetation trend. And you can also access this image in the QuantGIS. For the sake of time, I will not open it in the QuantGIS, but you can access any of the layers that we are showing here in the QuantGIS and navigate across it and analyze it. So, and so we read the data, and now we have this data just in the memory of my workstation. So, but I can save it. So I read directly from the cloud to like a memory environment, but I can save this as a GeoTIFF file, and I can have like a physical representation of this file. So it's a kind of way to download any part of the planet according to your interest. So again, it's a database functionality for raster data. And here I'm using this save raster function from EUMAP to save like a file in this location. So, and I will open this file just to explain that this is now like a output. No, it's here. So this is the file that I generated for the Matopiba, and this is an actual file. So I accessed this data according to my region of interest, and I downloaded it and saved it in my workstation. Of course, I can do it for all the time series and have a complete time series for the Matopiba region to, for example, do a land cover classification. So this is a way to access the raster data, but sometimes it's important to access, for example, for specific coordinates, it's important to access the time series signal. So here I will show how to access for 1 pixel, access all the images that we processed and plot a chart and create a chart with the same information that I presented in my slides. So again, I will use this WebGIS representation in the Python just to pick up some location, and I could select any place of the planet here because we have everything. And if you click here, so considering this location, this is the longitude and latitude. And of course, if you have like your own coordinate and coordinates, you can just read it as a CSV file and iterate of all the coordinates to retrieve the time series analysis. And here, using this coordinate, I'm accessing like this image here, so you can see the data that I'm accessing, and this is the pixel value. And the pixel value is 5,000, but it's because we rescaled to fit in a better computational representation. So to have the values, the real values of an EVI across 0 and 1, you can just divide it by 1,000. And in this case, the EVI value here is 0.5. So now I'm using, like, again, one function that I developed here. So I will not explain in detail this function, but it's just a function that will get the longitude and latitude, access this longitude and latitude, and retrieve the all the pixel values of the whole time series here. So 126 states. So it takes a while. It's doing parallel because it's accessing multiple files, but it's a remote access, so it takes a while. But you have, for this coordinate, you have all the pixel values here in this column. And this is a tabular representation of the Python environment, and you can save it as a CSV file. And you have this as output. So it's the same representation. I just saved it as a CSV. And the last part is use this function to access for this coordinate, I'm accessing the gap-filled data and the deseasonalized signal, so just the trend, and I'm performing like the ordinary least square regression over just the trend, and we can see the result here. So it's important to explain that the gap-filled data, the blue line here, it's pre-computed, and the trend, it's also pre-computed, but you can see here that it's possible like inform different different years, and for these years you can change it, and it will run the analysis again. So the ordinary least square regression is processed on the fly here. We have the image, but you can play with these parameters and, for example, change the period just to check the result. So, and I will just pick up a random location here to explain, like for another place. And again, you have a new coordinate, and you can run the analysis again. So now it's a new coordinate, and you can play with these years. And here you almost know it's not possible to see like any like a visible trend, and you have the regression parameters here. So this is what we have now available. So for EVI mode 13 key one and Cloud Optimized GeoTIFF, and really fully accessible. And I go back to my presentation. So what are the next steps? So we are working R tutorial. So again, this is a kind of raster database where you can access any pixel of the planet, processed according to the workflow that I presented. And of course, you can do it in your favorite programming language, as R, for example. And considering like this is related with the technical aspect, and we are also working like possible validation strategy. So we performed a gap filling operation, but it's important to measure how is this gap filling approach, if this gap filling approach is doing or not a good job. So we will simulate some gaps to understand if the gap filled result it's real, it's close to a real value. So it's we are working on it, and we have all these trend analysis results. And for some case, for example, we would like to validate it and see if we can actually detect some degradation signal or others like landscape process across this data. And it's important to explain that the land cover change here, it's not part of the approach, because we already have, like, for example, the BFAST to do it. And but at some case, in some case, you can have like a native vegetation, like a native forest. And if you convert it to like a tree plantation and silviculture, maybe you will not see any difference in the trend. But if you convert, for example, a pasture area for a crop area, maybe you will see a positive trend because of the bigger the increase in the values in the of the EVI values across the time. So according to the land use and the land cover, these trends can have different means. So we are analyzing it and try to understand it better. And of course, we coded everything, so we have a consistent workflow to process other vegetation index products. So we are working with the AVHRR. So it's a coarse resolution, 5 kilometer, but we have this data since 82. So it's a nice data set to capture the long-term trend. And we also we have plans to process the Proba V. It's a better spatial resolution, 100 meter, but it's a small time series, so from 2015 to 2020. But we want to have all these vegetation index products organized in a consistent way, as I presented here, to modes. And we will make this data set available to OpenLandMap. It's our web viewer, our web GIS. So we have several global layers there. And it's a nice tool to access and to see, to have like a quick visualization of the product. But to do a proper analysis, we recommend, of course, access the data as I presented here. And we want to put all this together in a manuscript. So we are working on it too. So we have a publication coming. And here I finish my presentation, and I'm open to questions. And again, thank you for the opportunity to give this talk.
Hello, Leandro. We have to thank you very much. I thought we would have a talk, but instead we had an actual workshop, hands-on workshop, a great lecture. I have been impressed with all the work you have been doing, with all the work that the OpenGeoHub Foundation is doing. But now I don't know which word I should use to describe my feelings. I'm really excited because in addition to a great presentation, to a great talk, the OpenGeoHub Foundation, through you in this case, at this moment, is actually offering us a great data set, and a data set that is really ready to use. I really liked when you mentioned that remote sensing data should be treated as a commodity. And I hope this day will come soon. And I think that the OpenGeoHub Foundation is actually doing that, is creating commodities out of the remote sensing data or remote sensing data sets, the many data sets we have nowadays available for the entire world. And this project is great. You know, so many thoughts came to my mind while watching your talk. So first of all, I'm really frustrated that Alfredo Huet, the person behind EVI, was not attending this talk. And I'm going to call him, write to him, because we need to present this to Alfredo Huet. Okay, I think that when the MODIS data was conceived back in the 90s, when the MODIS sensor was launched aboard the Terra satellite in early 2000s, I think that everyone who worked in the MODIS project, in the MODIS team, as Alfredo Huet, dreamed with what you presented today. A data set ready, clean, easily accessible. And so I think that for me, it's like a dream coming true. I want people from SatVeg, from Embrapa, you know, the SatVeg, the satellite vegetation, Alex, Coutinho, Julio. I want them actually, not only I want them to watch this presentation. Actually, I just wrote Alex, saying, you need to see this, because what you did was a global set vec. And but I would say that more than putting data together, there is a whole new concept behind. Because, for example, removing the seasonal component from the data, the noise from the data. So you really have a data that is very clean, not only cloud-wise, but semantic-wise, the signal-wise, in terms of semantics, in terms of meaning. So we really can, in a very quick way, retrieve the trend, what is happening with the Earth's surface. I mean, you know, when you showed some examples for Brazil, and you showed that, for example, the northeastern region of Brazil, you see some signs of land degradation. And came to my mind, it reminded me of the COP26 last week in Glasgow. I would say that one of the key messages from the COP26 was that we need to pay more attention to land degradation. Land degradation is a key issue for the world today. We talk too much, or we need to talk too much about carbon and emissions, but we also need to talk about land degradation. Because if we want to reduce emissions, we need to optimize the use of the land. And that means that we need to know more about land degradation processes. And what you are providing us is a very quick tool to see where land degradation is more likely to occur, is more likely to be occurring. So, in fact, you have more than a great data set, you have a great tool. I'm really touched. I'm very emotional because this is very beautiful. So I really want to share. I really want to share. There are so many people that came to my mind who need to see this presentation. So, and this is actually the beauty. I always say we are going through these very tough pandemic times. And I say that the pandemics did no good. I mean, when I think about the pandemics, I see sadness, I see suffering, I see pain. However, the challenges imposed by the pandemics made us stronger and more creative. And I see that, I think that the world after the pandemics will be different. For example, it will be easier for us to interact. You are in the Netherlands, Eliana is in Rio Grande do Sul, I am in Goiânia, and we have people here from Iraq attending this session. So I think this will be one of the legacy of the pandemics. Not of the pandemics. Pandemic is no good, but of the strength that we had to put together to face the challenges imposed by the pandemics. So this session, your talk, your lecture, your workshop will be saved for many other opportunities, for many other people, because people really need to know about what you did, about what the OpenGeoHub did. I'm really enthusiastic. I'm really excited. Well, before sharing the floor with Eliana, I have one question. Well, and of course I have an invitation. I don't know if you know already. I think you already know you're going to give us a very good hands-on workshop. We need to, I know that you're coming to Brazil, you need to give a lecture to these groups here. But anyway, Veraldo, you just mentioned before we started that we need to have IGARs in Brazil. Now I have no doubts, so count on me. Leandro, one quick question. What about data continuity? In other words, we still, MODIS data, MODIS sensor is still operational. Until when? Do you know? And, okay, the OpenGeoHub gave the world this great product. Can we count on this product until MODIS continues to be operational? For example, next month, next year, what are the plans of the OpenGeoHub? And I don't know if that is part of the plans of the OpenGeoHub Foundation, but if not, I give you a suggestion. I think you know me, I like to give suggestions. I don't know about MODIS. I really am not aware of how long more MODIS will continue to be operational. But after MODIS dies, I mean, we have MODIS on both Terra and Aqua. But after MODIS is gone, do you think that we can continue this data set, this really ready to use data set with VIRS data, with other data sets? And that, I think, involves more than assuring that we have access to data, that needs to consider data continuity issues. So what are the plans? So those are my questions. I see that Manuel from LAPIG put some question here. And but before, I don't know if you'd like to answer my question, or Eliana,
Yeah.
I don't know if you'd like to make some comment before that.
Yes. Leandro, you would answer the question from Laerte before?
I think it's better to answer the question now. So thank you, Laerte, for to talk with so enthusiasm about the work that I presented here. And so, yeah, that's a very nice question, because I don't know till when we will have MODIS. So it's important to think in a data continuity strategy and how to integrate, for example, other new generation satellites to this product. So the plan is really, we were really focused in create this workflow and have it up and running. And now we have the infrastructure and the approach implemented. So after that, we plan to integrate with new satellites as Suomi NPP and VIRS sensor and the Sentinel-3. But we need to first check and see, because all this product was processed considering just one sensor. If we have, like, for example, an overlap between sensors for a specific period, probably it's better perform the harmonization before the gap filling, because we can use like real data from different satellites to fill the gaps and later do the gap filling. So, but the main challenge here is really implement these harmonization. We did some experiments with like machine learning approach. So we are using, for example, a random forest to correct the past AVHRR data according to the modes. So we are performing this data continuity experiments in the past data, but we can also we tested also like a deep learning approach, like recurrent neural networks, to analyze, for example, the signature of the vegetation index and predict like what would be the response of that sensor of that product, considering a different sensor. So there are some strategies, but mainly we are focusing this data harmonization, considering data-driven approach and machine learning approach. And of course, we can also process it for other bands. So that's an important point, because we already downloaded the Mode 13 key one. So we have all the bands here. So it's easier that step in the workflow to download from Google Earth Engine. We can skip that and we can process like internally. And so we have these two streams of work up forward.
Great. Sorry, Eliana, just one quick remark. I see a great future for this data set. This is a science paper. Because, okay, I understand that we can rely on the OpenGeoHub Foundation. We are going to have this data set. We are going to have the continuity of this data set. But, as you mentioned, I think that we need to look forward and we need to look backward. We need to continue to extend this data set in the near future, and we need to go back in time prior to modes, using, for example, AVHR data. So just imagine looking at the world, at the behavior of the global vegetation since 1985, since the early 80s, up to now. What happened to this world? I think this is a very strong message now that we are dealing and we are suffering so much with the effects of the global environmental change, of the global climate change. So I think this is a very strong message. Sorry, Eliana, I give back to you. Thank you.
Okay, Leandro, thank you so much for your presentation. It's very useful tool, really. I have some question from myself, and then I will read from the audience. For the time series, you use only a point. Can we use an area and take the average EVI time series for choose a select area or instead of point?
Yeah, that's a nice question. Yes, because for example, you could have like a crop area, like or even a whole farm, and you can access this, because when you have this cloud optimized GeoTIFF file, you have the internal structure of this file. It's in tiles, so you can access like just a chunk of the data and have the pixels that are inside of a specific polygon, for example. And using this polygon, you can perform like a spatial statistics and a spatial calculation, like an average or a maximum and minimum value, and you can derive, for example, like a temporal signature for a specific area. So I could like expand the tutorial to do it. Actually it's a nice suggestion, because it's just a way to access and retrieve this data, as instead to have a point, you could have like a three-dimensional structure with several pixels in the space and like a third dimension with the time.
Yes, thank you. It is very useful to analyze an area or standard point. So we have some questions from Manuel. Manuel asking, considering the long-term time series you presented and all the code and workflow approaches, do you think possible to monitor areas under environmental recovery in Brazil, performing ecological and or CO2 absorption analysis, for example?
Yes, this is. I think it's possible, but there are some. I think it's more like a kind of limitation. So what we are doing here is considering all the pixels we are processing and organizing these different metrics of the trends and different metrics of the regression. So we have like a slope, we have like this R square with the trend, so to indicate if how the regression is performing for that specific pixel. But using just this information, I think it's really difficult to do like a proper monitoring of this environmental recovery. So this data, it's a kind of base data set, but you need to rely on other data sets. So you could have like a land cover, and considering, for example, this land cover, you can just analyze for stable areas what are the trends, or you could, for example, for pastury areas, you could analyze what is the temporal behavior of this, all the pastury areas, for example, in a biome or in a municipality, and see what pastures are better and than others, considering, for example, the average of the region. So this is because this trend, it means different process in the landscape. So it's really important to have other data sets to understand the meaning of this trend. So I think the main point is here, but it's that. But considering, for example, other data sets and more information, we can understand better what is the meaning of the data that we are producing here.
Okay, thank you. And another question from the audience: if we can expect the same code for higher resolution products like a Planet or Sentinel?
Yes, in this workflow, we aggregated by every 2 months. So, and there is like a clear relation. If you, for example, if we aggregate by month, we will have much more gaps to fill. But if we aggregate, for example, by 3 months, we will have less gaps. So this aggregation window, of course, it's a parameter of our workflow, but it will change considering each of these satellite products. So, for example, with Planet, we have like daily data. So, and we could use it to the Planet data to perform the same workflow, and Sentinel also. But specifically for these two products, Sentinel and Planet, the main issue here is the cloud detection. So we don't have like a reliable way to identify the clouds with high confidence. So, and we are using like some outlier detection in the time series domain to identify what are these spikes in the time series could mean, like a cloud or a cloud shadow. But specifically the same workflow for these two satellites, technically speaking, it's possible, but the product probably would be more contaminated with clouds. So we still need to improve and create new ways to identify clouds in these two satellites. And it's tricky, being challenging, because you don't have like the thermal band to identify the temperature of the cloud. So, and you have just these bright pixels that could mean different things in the landscape.
And maybe the technique is using the maximum EVI value can eliminate the clouds and the shadow, but maybe we lost some information. It's a trade-off that needs to be tested, maybe, isn't it?
Yes.
Okay. And in fact, the bi-monthly time series was chosen by testing before to eliminate the gaps, or it was taken from some paper, some literature review?
No, we did some tests, but because here we are using the 16-day product, Mojis product. So if we just do bi-monthly, it would be like just 1 or 2 observations. So to increase the chance to have a real observation for the pixels, for a specific pixel, we expanded this window, but we did some tests. So for example, in Amazon region, you have multiple months without any observation. And we also use it like a flexible, like a not a too strict criteria for the pixel reliability. We could, for example, remove more pixels and keep just like the pure EVI signal. But we selected like we removed just the pixel reliability equal 3 to improve the chance to have more data, real data, and we performed this artifact detection, this outlier detection to remove the remain cloud pixels. But it was more like a sensitivity analysis considering some cloudy regions in the planet.
Perfect. Well, I have no more questions. In fact, I have many questions, but first I need to try by myself this data set, and after I will ask many questions for you, Leandro. But for now, I have no more questions. I don't know if Laert have some more questions or more considerations, please.
Yes, Eliana, thank you. But I would like, before I do my final considerations, and actually I needed to acknowledge the OpenGeoHub Foundation. I forgot to do that at the beginning of the talk. And I see that José Marcato Jr., he put 2 questions here, or 1 question. First, he said, great presentation, Leandro, but do you plan to conduct a merged analysis between your data with temporal land use, land cover from map biomes, for example? Well, José Marcato and Leandro, before you answer, José Marcato, the acknowledge I have to do, it's a very important acknowledgement, is that this data set that the OpenGeoHub Foundation put together, this Mojis data set that Leandro is working with, in a very nice way. I mean, that was very generous from the OpenGeoHub Foundation. We already used this data set to produce the pasture quality analysis from 2000 to 2020 within the scope of the Map Biomes Collection 6. So, José Marcato, I'm not answering your question. I leave that for Leandro. But I would say that this data set is already being used within the scope of Map Biomes. And I hope that this collaboration between Map Biomes and the OpenGeoHub Foundation becomes stronger because we have many things to do. And I would make a comment before giving the word back to Leandro that I think that after COP26, we really need to create a data set similar to this one, and I go back to Manuel's question regarding older satellites or higher resolution images. And I would say that we need to have a data set like the one that the OpenGeoHub put together is openly and freely offering the world. We need to put a data set based on Landsat data, for example. I know that the University of Maryland, they have what they call Landsat ARD, Analysis Ready Data Set. But I think that we need to go beyond the data set, the normalized data set, and we need to create, based on Landsat data, products like the ones that Leandro showed us. Because those products, I mean, if we think about COP26, the world we need a global baseline. I think that when we talk about degraded lands, when we talk about carbon market, we need to talk about baseline. And of course that the OpenGeoHub Foundation is providing us with a very nice global baseline. But I think we need to improve in terms of spatial resolution. So I think there are a lot of work to be done. And I hope that the collaboration between Map Biomas in Brazil or Map Biomas Network and the OpenGeoHub Foundation gets stronger, and with many other products to be worked together, to be produced together. Leandro, but I give you the word to respond, to answer to José Marcato, and I see that Tom Hengel from the OpenGeoHub Foundation put some comment here that Leandro can comment on the comment from Tom.
Okay, so yeah, specific about this usage of temporal land use and land cover maps, for example, for map biomes. I think this is it's really important. Use these products to improve the understanding of this data set. So, for example, if you think in the way that the BFAST works, it tries to identify in the time series, it tries to identify a breakpoint that could be changing in the season, changing the trend, but it's mainly related with, for example, the land cover change. So what we are doing here, it's actually just analyzing the long-term trend, but we could use, for example, land cover products. We have several land cover products, global products, like regional products, and we can analyze and access this data to understand where the land cover change in this time series. And we can use this data set, these maps together to perform, for example, a subsequent analysis to understand what are the trending before the change and after the change. So it's really important, realize and use this data to understand. Or, for example, we could analyze how the vegetation trend is changing, for example, in the Brazilian biome. So if there is considering just the vegetation, for example, for the different biomes, if they present different trends, but we need to have this map to identify the vegetation. So here we have just this base product. It's a kind of baseline, but to create like a proper environmental analysis and derive it, it's important to combine this product with other, for example, land use and land cover maps. And about the comment of Tom, so yeah, I mentioned it, but we use this stack register. So it's a kind of new protocol to provide like several raster data in a really nice way. So stack means like spatial temporal asset catalog, and now we have like different catalogs across from different organizations. So, for example, you have the Landsat archive available in the Amazon AWS, for example, the cloud provider, and you can access it through this protocol. So this is a kind of future trend, and in the way that we will access like raster data in the future years, I think. So the way that I presented here, it's important to put it available in a stack register to provide more metadata about every processing steps and different, for example, pixel resolution and methodological aspects. So we can have in this catalog and the data and a comprehensive metadata information about the product. So we will organize it for the future also.
Thank you, Leandro. So, Eliana, would you like to say a few final words before we end the session? And I would like to make some final comments after you.
Okay, thank you. Leandro, thank you so much. It's very different, a very useful tool that you develop. Thank you so much to present for us here. I hope that everybody can be used and can be take advantage of this very great work. Thank you so much.
Thank you, Eliana. Thank you very much, Leandro, for this great talk, this great presentation, actually a great workshop. And I would like to mention, I would like to congratulate the OpenGeoHub Foundation for the great work it is doing. And I would like to mention as well that the OpenGeoHub Foundation truly believes in open science. So, and I have a big consideration. I really believe in open science. We do open science here at LAPIG, the image processing GIS lab at the Federal University of Goiás in Brazil. So I'm a very big fan, enthusiastic about open science. And that is what the OpenGeoHub Foundation is promoting concerning remote sensing, Earth data sets, remote sensing data sets. So congratulations to the OpenGeoHub Foundation for this great work, these great products, and for making these products available to everyone. And not only the products, but the codes used to produce the products. So I think this is the way that we need to move on. This is the way that we need to collaborate. I believe in collaboration. I believe that when we share knowledge, we share resources, and actually, and more important than knowledge and resources, but we share or code, we share different perceptions about the problems we face. And pretty much the problems we face are basically the same. I mean, we are talking about global issues. So I think this is the way that we need to move on. We need to really do the science and do our work. So thank you very much, Leandro. Congratulations on the great work. And I really hope to strengthen the collaborations between MAP Biomas, between LAPIG and the OpenGeoHub Foundation. A great work, a great talk. I thank you very much, everyone that attended this session, and it will be available through YouTube for everyone. And please share the YouTube link with your colleagues, because I believe that many people in Brazil should attend, should see this presentation. Thank you very much. Thank you, Veraldo, for the opportunity. Thank you, Eliana, for chairing this session. And Leandro, we talk soon. Thank you very much. Bye.
I think that we need to ask for the José Martins to answer this session.
To close the session. Okay.
Yes.
All right, José Martins, we are ready to close the session.
Hello and greetings to all, and thank you, Leandro Parente, one more time for your great presentation using Python with the models that are set to plot the timing series of the vegetation of the world. In the next presentation, we will have, I think that Leonardo needs to put the folder in the tela. It's not showing the YouTube. Now it's showing. In the next presentation, we will have a SAR presentation. This is a different kind of sensor. Mode is uses 36 bands, but it is a passive sensor. The SARS is an active sensor that works with sending the signals to the surface of the Earth and capturing the reverse signal. So is it able to capture details of our top of the canopies, is able to a more shape related data. So it will be our next presentation, and I hope that we can see you all there. Thank you.
All right. Thank you, José Martins, Eliana. Thank you very much, Leandro. Congratulations on the great work. Bye, everyone.
Thank you.
Bye-bye.